Hi, this is Kevin Emery with Quantum Easy. Thanks for tuning in. Today we're going to take a quick look at the code itself that generates these histogram or bar chart plots of our quantum computer execution results. As always, we go to Google Colab, C-O-L-A-B, and you hit New Notebook. Now I'll put the code in the description of the video and you can paste it right in here to your new Colab notebook. But let's take a look at what it does and how it draws this graph. So the first thing we do is some pip installs of Qiskit, which is our quantum computer programming language library, qiskit.AER, which is our quantum computer simulator, and pylatexenc, which we use to draw the circuit. And then we import the necessary classes and methods from those libraries and get into the core of our program with the statement circ equals QuantumCircuit 2, 2. Circ is just a variable, we can call it whatever we want. QuantumCircuit is the constructor, which takes a number of qubits as its first argument, and then as an optional second argument, it can also include a number of classical bits. In this case, we want to give it 2 qubits and 2 classical bits to store the measurement results from when we measure those qubits. Then we pass the qubit 0 into an H gate. 0 doesn't necessarily mean the qubit contains a 0, it's just the qubit at index 0 or Q0. So we pass our Q0 into our H gate to put it into a superposition. That's like Schrodinger's cat, the cat in a box that's both dead and alive at the same time. Then we call a CX gate, or a controlled X. Now the CX gate, when we mouse over it here, you see it takes a control qubit and a target qubit as its argument. So the first one is the control qubit, which we just put into superposition. The control qubit makes the target qubit match. So because this target qubit started out as a 0, then if the control is a 1, it'll flip the 0 to a 1. If the control stays 0, then this qubit will also stay 0. So they always match. And so when you put it in superposition, the result is that this target qubit also gets put into a superposition. But it's entangled with the control qubit because once it's measured, they have to both be 1 or both be 0. And that's the essence of an entangled superposition state. So then the next thing we do is measure it. Okay, circ.measure. This, just like the constructor for QuantumCircuit, where we put the quantum bits first and the classical second, so this array is the quantum bits, and this second array is the classical bits. Now it looks at the indices of the array. So the first element in the array for the quantum bits matches to the first element of classical bits. It measures qubit 0 into classical bit 0, and it measures qubit 1 into classical bit 1. Then we run the code on our simulator. AerSimulator is the more up-to-date version of the simulator. So we put that in a variable called simulator and called .run, and we pass it shots equals 16. Now that's the number of times that we actually execute the program. I made another video explaining why it is we need to run a quantum computer program more than one time in terms of physics and the insights of John Bell. However, just for the purposes of understanding the code, we need to remember that the higher the number of shots, the more accurate the execution will be. With only 16, we see a lot more 0-0s than 1-1s. Roulette players who bet on green will be thrilled, but it's not a very accurate representation of the probabilistic nature of our circuit. This circuit should produce an equal number of 0-0s and 1-1s as the number of times that you measure it approaches infinity. And in fact, if you're lucky, we could have gotten 6 and 6 instead of 12 and 4. Sometimes it will be exactly equal. If we give it a larger number of shots, it's almost like zooming in on the circuit so that we can more accurately see the distribution of probabilities that it gives rise to. Then we take the result from the job and put it in a variable called result. Very creative, that. And then we call get counts on the result, and we display it with plot histogram counts. The display keyword isn't strictly necessary if plot histogram is the last line of your program, but I like to draw the circuit as the last line of the program. So explicitly what this line of code says is display a plot histogram of the counts and give it this title. So in order to get a more even distribution on the bar graph that's representative of the nature of this circuit, we've increased the number of executions to 65,536, and we'll run it again. Go, go, gadget, quantum run. You can do it now. As soon as it's done executing, we'll see a much more even distribution between the double zeros and the double ones at about 32,700 to 800 each. And this is much more representative of the actual mathematical probability distribution that our circuit represents. If you'll forgive my singing and tune back in another time, I appreciate the attention. The quantum graph we have here will get much more interesting as time goes on, because we're going to add in some additional bits that aren't entangled, and they're going to mix together in the same circuit with some bits that are entangled, and we'll see how that affects the bar chart as we add more bars to it.